Let's jump right into this explainer. Picture a typical industrial drain, just pouring this dark, contaminated wastewater directly into a river. Now imagine a glass of crystal clear water right next to it. What if I told you the high-tech filter capable of turning that first toxic mess into the second was actually made from another mass of highly dangerous industrial waste? Honestly, it sounds a lot like modern-day alchemy, but it's happening right now.
Today, we're diving into a really radical waste-to-value framework. We're going to see how two completely distinct industrial hazards, toxic coal ash on one side and contaminated wastewater on the other, can actually be engineered to neutralize each other. It's a pretty wild concept.
To truly wrap our heads around the immense stakes here, we really have to look at the sheer scale of the problem. Consider this. In just the year 2016, India alone consumed over 966 million tons of coal. And across the wider region, including neighboring Pakistan where coal-based industries are rapidly expanding, burning this much pulverized coal in thermal power plants generates literal mountains of mineral residue. This residue hardens into ash, creating just an astonishing volume of solid waste that we have to put somewhere.
And traditionally, this fly ash, which is the fine, powdery stuff that rises with the exhaust gases, is viewed as a severely virulent pollutant. It is absolutely laden with heavy metals. We're talking about the heavy hitters here: arsenic, barium, cadmium, chromium, lead, mercury. If this ash is just left unattended in storage ponds or landfills, it threatens to leach directly into our groundwater. Or worse, it becomes airborne, potentially causing severe respiratory, neurological, and cardiovascular disorders. It is, by every definition, a massive liability.
But things get really interesting when we use a scanning electron microscope to zoom way in on a piece of this treated coal waste. We don't see a solid rock. Instead, we see what are called cirrospheres. They are microscopic, super lightweight, hollow spheres made out of alumina and silica. If you look closely at the highly porous surface, it's basically like a microscopic sponge completely filled with these tiny, intricate tunnels and cavities.
Because of all those tunnels, the fly ash has an absolutely enormous internal surface area, which makes it absolutely perfect for adsorption. And yes, that's adsorption with a D. It acts just like a molecular magnet. As contaminated industrial wastewater flows through this ash, you can actually picture the toxic heavy metals and pollutants getting completely snagged. They get physically and chemically trapped right on the walls of those microscopic pores, like little color-coded dots getting stuck in a maze. But the engineering innovation doesn't stop at just dumping raw ash into water. Researchers are taking this a huge step further. They are physically spinning this fly ash together with polymer solutions using a really fascinating technique called electrospinning. Basically, an electric force draws charged threads of this ash mixture out into incredibly fine fibers. The end result? An advanced nanofiber filtration mat with a massive surface area that is exceptionally good at capturing volatile organic compounds from both air and water.
And the research absolutely backs this up, confirming that converting this discarded, hazardous solid waste into high-tech environmental filters is an incredible leap forward. We are literally taking a liability that costs millions to manage and dispose of and spinning it into an invaluable environmental asset.
Now you know and I know that this isn't just about saving the environment. For industries to actually adopt new wastewater tech, the economics have to make sense. It has to be a win for the bottom line too.
And when we look at the cost comparison, the business case is undeniable. Traditional, high-grade, commercial activated carbon? That can cost upwards of $21 per kilogram. Processed fly ash derived from waste slag? Roughly $0.009 per kilogram. That is a fraction of a single cent. Think about places like Pakistan, where industrial wastewater management is becoming a huge regulatory concern. Local coal-based industries could completely flip the script. They could turn their massive ash disposal liability into a highly lucrative product line, selling cheap filtration media directly to local textile mills.
Okay, so you might be thinking ahead here and asking a very crucial question. Once this super cheap fly ash acts as a filter and becomes completely saturated with all those toxic heavy metals from the wastewater, what on earth do we do with it? How do we safely dispose of a filter that has basically become a concentrated sponge of pure toxins?
To answer that, we really have to differentiate between two types of reuse: unencapsulated and encapsulated. Unencapsulated reuse is highly problematic. This is when loose ash is scattered directly back into the environment, like, say, using it to melt ice on winter roads. The toxins can easily leach right out into our surface and groundwater. Encapsulated reuse, on the other hand, is the safe path. This involves physically and chemically binding that saturated ash into solid structural materials, like concrete or bricks.
Think of the encapsulation process exactly like a lock and key. By taking this toxic, heavy metal-laden coal mud and solidifying it into cement and fine aggregates, those dangerous elements are permanently locked away. They are essentially sealed within a structural vault. It creates an amazing dual-use scenario where we safely manage our waste while simultaneously creating foundational building materials. The chemical bonds simply prevent the heavy metals from ever washing out into the environment.
Extensive testing proves that this solidification minimizes metal leaching so effectively it completely meets strict national safety standards. We aren't just disposing of the waste, we're actively using it. And honestly, here's the best part. Adding this coal mud actually produces a lighter weight brick. If you work in construction, you know that a lighter, structurally sound brick is highly desirable in the industry.
Which brings us to the ultimate synthesis of this entire concept, what we call the triple bottom line. First, we clean toxic industrial wastewater at a tiny fraction of the traditional cost, using a waste product. Second, we safely dispose of that hazardous coal ash by locking its captured toxins securely away. And third, we manufacture functional, lightweight building materials from that locked waste to build our cities. It is quite literally a perfect closed-loop cycle of efficiency.
So, as we wrap up this explainer, I want to leave you with one final thought to chew on. We've just seen how mountains of highly toxic coal ash, a material that historically causes massive environmental damage, can actually be engineered to purify our water and build our infrastructure. Look around at the industrial byproducts we carelessly discard every single day. What other waste is out there, right now, just waiting for its own technological alchemy to become our next greatest resource?